Thanks a lot, Marika, for accepting our invitation. Marika is the co-leader of the working group one of CosmoVerse, and she's currently at Hull University in the UK, was previously a postdoc at Edinburgh University, where she also obtained her PhD. And Marika's research topic is observational and statistical cosmology with probes of the large-scale structures. Today, she will present the cosmology with kids. Marika, you can start please when you're ready.
Okay, thank you very much, Eleanor. Well, hello everyone. Good morning, afternoon, evening, wherever you are. So as Eleanor said, I'm going to talk about cosmology with kids, or the kilodegree survey. It's a weak gravitational lensing survey. And we probe the large-scale structure with it. So I'm gonna give you a bit of background about weak gravitational lensing and in particular cosmic shear, summarize the KIDS 1000 core cosmology results, but then I will focus on everything that happened after that and highlight some of the work which is relevant for the final KIDS legacy analysis. Okay, so a little background then. So gravitational lensing and cosmic shear. In this little picture, I'm going to explain how that works. So imagine you have galaxies that are far away and their light passes by massive structures. And as a result of that, the path of light is distorted, which means that the images that we see of these galaxies are also distorted. Now, if we have two such galaxies in the background, and their light passes by similar structures, they will be similarly distorted, creating a correlation between their shape of their images. And this correlation is what we measure as the cosmic shear signal. Now, how much distortion we get depends on how far away these galaxies are from us, because the further away they are, there is more intervening matter and there's more lensing happening. Okay, so this is cosmic shear in a nutshell, but let's see how it works in practice. So in practice, we can't really measure the shape between the correlation between the galaxies because the signal is much lower than the intrinsic shapes of galaxies, so the shape noise, which is called the shape noise. And we can only measure this signal if we have tens of millions of galaxies. So we need very high resolution and deep images to be able to measure anything. We also take multiple bands to get the colors of the objects in our catalog. And together we create a catalog of galaxies and stars and all the objects. And we use the colors to separate galaxies from stars to make a catalog of galaxies. And once we've done that, we can measure the shapes of galaxies and also use these colors to estimate the redshifts. And I will talk a little bit about that later. Now, these two components are the main two things we need to measure to be able to estimate the signal. And both of them need to be measured very accurately. Now, the thing is, because of noise and other effects, it's difficult to measure them completely precisely and accurately, and we need to calibrate them after the measurement. And these calibrations happen using simulated data or image simulations for shapes, and then we have mock data from embodied simulations for the redshifts. Okay, now once we have information, we can divide the galaxies into redshift bins to get the evolution of matter, and then measure the signal by correlating the shapes of galaxies in the same redshift bin or between two redshift bins. Now we have the signal, we need to have a model to compare with it. Now you can choose any cosmological model that you want, but usually it's a standard model, flat lambda CDM. But the model directly doesn't give you the results, so you have to be able to model the large-scale structures. And usually people either use analytical models, such as the HALO model, or directly use numerical embodied simulations. So using that, we can model the signal and also the error. but we need to get the redshifts of galaxies as an input to be able to model that. Because as I said, the further away the galaxies are, the larger the signal. But before we can compare the actual signal with the modeled signal, we need to take care of nuisance effects. And the nuisance effects such as intrinsic alignments of galaxies, which can mimic cosmic shear signal, because galaxies could be intrinsically aligned because of the physical processes when they are formed, or baryon feedback, which can happen because of active galactic nuclei and jets pushing matter around, so that changes the matter distribution on smaller scales, or effects such as uncertainty in the calibration of the two components here. So once we have all of these, we can do a likelihood analysis, compare the signal and the model, and do our inference. Now, before this picture is complete, I want to point out another thing that's very important, and that is blinding. Because as you can imagine, this process, which is a cartoon version of what actually happens, has a lot of steps, and each of these steps have their own steps inside them. And in each step, you can make some decisions of what to do. And you don't want these decisions to be based on what you want to get at the end. And this can be a subconscious thing, so you don't have much control over it. So it's very important to blind data and only unblind it after the inference is done. And this is what we've done for kids as well. All right, so a little bit about kids. Kids is a weak lensing specific survey. It means that it has very good seeing, which makes the shape measurement easier. And then kids combined with his sister survey, Viking, they have 9 photometric bands. And this means that we can have a better estimate of the redshifts of galaxies. So there's 9, might not sound very big, but for weak lensing surveys, that's a large number. So what we've analyzed so far is 1,000 square degrees of data, which includes 21 million galaxies after all the masking is done. But the survey is completed, so we have collected all the data, and we are in the process of analyzing the rest of it. And I can't tell you exactly when it will happen, but sometime soon we will have the final data release. Okay, so I said that I will talk about calibration a little bit. So first of all, shape measurement. So this is what happens typically. You have a galaxy that looks like this intrinsically. Then you have gravitational lensing happening on it, and you get a shear. Now, this image of galaxy is this is a very big galaxy. Normally what galaxies we have are much smaller than this, and the shear that you get is much smaller than this, so you won't be able to even see it by eye. But it is a cartoon version, so it's better to have it more exaggerated. Okay, so it's sheared, and then it goes through atmosphere or the telescope, and a convolution happens, so it gets blurry. And then we have we have to make it pixelated because of the CCD. And then finally, there is noise in the image. So the thing that we measure is something like this. But the thing that we want is this one. Now, how can we get from here to here? So the way we do it is by looking at stars. So if we can identify which objects in the catalog are stars, then we can reverse this process. So we know that stars should be intrinsically point sources. And when atmospheric effects happen, they get a convolution and they get blurry and they get bigger, and then pixelated, and then we have the noise. Now, because we know what this should look like, we can make a model for this point spread function, or the scene. And then once we have the model, we can correct the shapes of galaxies. Now, this needs calibration because sometimes we have galaxies that are blended with each other. Also, the noise is not the same everywhere, so it's difficult to model that. And to do that, we make image simulations that have all these effects in them, but we know what this shape is supposed to be. We run them through the whole process and then see if we get the input back. And if we don't, we use that correction in our data analysis and the uncertainty on it. Okay, so that's the shape measurement part. Now, what about the redshifts? So imagine you have 4 photometric bands. So these are shown here, UGRI. These are actually the bands that KITS has. And then you have a galaxy with a spectrum that looks like this. So you can see that there is a prominent break here. And currently, the redshift is at, the galaxy is at redshift 0, and this break is in the U band. Now, if you move this galaxy to redshift 9, the break moves to the I band. I can imagine if I move it further, it's going to be outside of these 4 bands, and then it's going to be difficult to tell what the redshift of the galaxy is. But because we have Viking, which adds another 5 near infrared, we can actually go to higher redshifts. So these are the extra 5 bands from Viking, and they're positioned in where the atmosphere has these gaps where it allows light to go through. And now if we push the galaxy to redshift 1.2, for example, you can see that we can still see the break. And this allows us to also break degeneracies between galaxies which have different SEDs. And because we don't have so many bands, they might look the same, but they might be in different redshifts. All right, so photometric redshifts also need to be calibrated. Here I'm showing the 5 photometric redshift bands for KITS. So this is the lowest band, this is the highest band here. The method that we use for calibrating is basically comparing our photometric galaxies with a subsample that has spectroscopic redshift, and then trying to match the properties of the two to get the redshift distribution. And the method we use is a machine learning method called self-organizing maps. And we also remove any galaxy in our sample that doesn't have a good match in the spectroscopic sample and create this thing called the gold sample. Now, the redshift distribution that we get after doing this process is shown in red, which is right under the blue almost. You can see it in the third bin a little bit better. And then we have another method which is complementary, and that's called clustering Z. But it also uses spectroscopic galaxies, but instead of looking at the redshifts of the galaxies, what we do is we actually measure the clustering signal. They were at the same try to fit the red curve to the black points using just the shift parameter, we get the blue. And you can see that the blue is almost on top of red for all cases, aside from bin 3 maybe. And the shifts that we see here are very small, so they actually don't have any effect on the results that we have. So we have 2 methods and they give the same result basically. Okay. All right, so now I'm gonna summarize the core cosmology results before I move on to the newer stuff. Okay, so cosmic shear, this is the correlation functions for galaxy shapes. We have the 5 redshift bins, and all their combinations are shown here, and that's why there are so many panels. This is the lowest redshift bin, and then we go to the higher bins here. The signal increases, as you can see, So and the red curve is the model. And the model includes flat.cdm for cosmology, and then we have nuisance effects, intrinsic alignments, parent feedback, and the calibration uncertainties. And this is the best fit to the data. Okay, so I'm going to go back to the blinding a little bit again, just to make a point of it. So here, this is where we were 3 weeks before submission of paper. We had 3 blinds, A, B, C, and we didn't know which one is the truth. And you can see the Planck contours there, which is in red. So this is showing S8 versus omega m. S8 is defined up there. S8 is the quantity that cosmic shear can measure best. So, and we had actually a vote to see who wants which one to be the truth as well. And it was interesting to see the divide between people. And it ended up being blind C. But the point I wanted to about this is that this was 3 weeks before submission of paper. So I think it was very important to do this because there were 2 members in our group who were sure they were on blind, but one of them thought it was blind A and the other one thought it was blind B. It ended up not being that in either of them. So I think the blinding worked very well. All right, so it was blind C, and this is the summary of the results. So on the right-hand side, I'm showing all the 3 2-point statistics we used. So in blue, we have correlation functions that I showed you earlier. In pink, we have the Fourier space band powers, and in orange, which is at the bottom of all of the contours, we have Kusabi's, which is a statistics that is specifically designed for cosmic shear and works very well for that. And we have a 3 sigma or so tension with Planck in S8. All right, so how does it compare to other cosmic shear results? So this is showing the concordance between cosmic shear results, and I've put a guesstimate line, shadowed line here, so it guides your eyes. And what's important here is that the Planck results in red are on one side of all the points, but also that it's higher than all the other points. Normally, if we have unaccounted for systematics in the data, they tend to add power to the signal, which means that they would result in an overestimated S8. So they would bring us closer to Planck in this case. And the fact that it's always lower means that it's not an unaccounted for systematics in the data. So it's probably something in the modeling. It doesn't necessarily mean it's cosmological, it could be astrophysical, but it's unlikely that it would be something related to the data. All right, so since then, we've done a reanalysis of the cosmic shear data. So Gianluca used a larger set of calibration for the redshifts. So this was to check if the calibration of redshifts has anything to do with it. And you can see that, so this black one is the result that I just showed you. And these 3 are the new results using the larger calibration compilation. And you can see that actually the larger calibration compilation pushes S8 to lower values. So it cannot be the redshifts that's causing this. All right, okay, so what about combining it with other probes? So for the core cosmology analysis, we combined with BOSS data, that's shown in blue, and also with 2DF lens, that's in the south. And then you can see in pink, we have kids. So this is the kids footprint. So in the north, we have overlap with BOSS, but in the south, we don't. And that's why we're using 2DF lens, which is another spectroscopic survey, very similar to BOSS. So we can combine all of them easily. When we do this combination, we get 3 2-point statistics. That's why it's usually called 3 times 2 PT, this kind of analysis. So we get galaxy clustering, cosmic shear, and their cross correlation, which is called galaxy-galaxy lensing. All right, so and this is the summary of the results from that combined probe analysis. So in pink, you can see the cosmic shear results. Then in blue, you can see galaxy clustering from BOSS. And then in purple, you see a cosmic shear plus galaxy-galaxy lensing. And then once we combine all of them, we get the red contour. And then you can see Planck in gray as well. And this red contour, as you can see, has a similar tension to Planck as the cosmic shear one had. So it's about 3.1 sigma. So they didn't really change any of the results doing the combination. And we've actually done combinations with CMB lensing as well, and that also gives similar results. So it just makes this contour a bit smaller. So another thing we did during the core cosmology analysis was to look at some of the more popular extensions to lambda CDM to see if any of them can alleviate the tension. And aside from this one, which reduced the tension in S8, so that's WCDM, and W is the equation of state parameter for dark energy, none of them could reduce the S8 tension. So if you just look at this panel, you can see gray is Planck and orange is the combined probe analysis. And you can see that this is less than 3 sigma, so it's, I think, less than 2 sigma even. But if we look at another one of the panels, for example, the one for W and S8, you can see that the two contours are completely separate from each other. And this is around 3 sigma again. So all this is done is moving the tension into a different parameter. So it hasn't really solved the tension. So I can say that none of the standard extensions to lambda CDM can resolve this tension. All right, so now let's focus on the future. So what's going to happen with KIT's legacy? So we have 350 square degrees of extra data, and this translates to 17% smaller errors if it was just analyzed exactly as we've done for KITS 1000. But we're working on possibly adding a higher redshift bin, which means we'll add more data, and also this data is going to have higher signal to noise because it's further away, and as you remember, the signal is going to be stronger. So this should have an effect of an extra 35% on the error bar, so an extra 35% smaller, so on top of 17. Although this is an estimate from a Fisher analysis, so and at that point we didn't really know how well we can calibrate this redshift bin. Some of the other things we've done since then is to add another shear estimation method, because we relied on only single shear estimation method before. So with two shear estimation methods, we can also test if it is the shapes of the galaxies and might be causing the tension, for example. And we have included multiband imaging for our image simulation. So this should give more accurate results in general. And then the other thing that we want to really focus on for KIT's legacy is to have a KITS-only combined probe analysis instead of combining it with external spectroscopic surveys. Okay, so I want to talk about this last point of just KITS-only combined probe analysis. So to be able to do that, we need to go to smaller scales because the KITS area is small. And if we just stay on linear scales, we won't really get very much out of galaxy clustering and galaxy-galaxy lensing. So, and in order to go to nonlinear scales, we need to have a model that can model that, and a halo model is such model. So just a little introduction to how halo model works. We assume that all matter is in spherical halos. So this is the vanilla halo model. And then if we know how these halos are distributed, what is their profile, and how they are how they follow the matter distribution, so the halo bias, then we know how matter is distributed. And also, if we have bias tracers, for example, galaxies, if we know how these galaxies populate the halos, this is called the halo occupation distribution, or HOD, then we can model their correlation, so their power spectra. Okay, so that's all you need to model. But halo model has some shortcomings. Usually, it cannot model the power spectra very accurately. So the way we model power spectra with the halo model is through the one halo and the two halo terms. One halo term is basically looking at correlations within a halo, and the two halo term is looking at correlations between each two halos, basically. So you can see here, this is the power spectrum, and then you have the one halo term that's shown in red, and then you have the two halo terms shown in blue, and then when you add them together, you get the green line, that's the halo model prediction. And then on top of that, I'm showing results from a simulation called Dark Quest. So that's the dashed line. And you can see that by eye, it looks pretty similar. And I just wanted to point out that a halo model review that we've been writing should be coming out very soon, so watch out for that as well if you want to know a bit more about this. Okay, but let's look at the ratios of the simulations to the halo model prediction. Once you look at the ratios, you can see that it's not super accurate. It's not very bad, but it can be up to 20% wrong. This is just a case that I'm showing here just for comparison. So it can sometimes be worse than this. Now this is the standard halo model. And in the standard halo model, we assume that halos follow the matter distribution in a linear way. So they're linearly biased. And this linear bias, we assume that it's not scale dependent either. So it's just a constant that well, it's a function of the mass of the halo, but otherwise it's a constant. Now, if we include the fact that halos are actually not linearly biased with respect to matter, so add the beyond linear halo bias effect, then we get this solid line. And you can see that it is within 5% of the simulations. And within 5% is sufficient for analyzing data such as kids. And this is what we've shown in this paper by Constance Mahoney. So this was using mock data, analyzing galaxy clustering with galaxy-galaxy lensing, and then including nonlinear halo bias. And the nonlinear halo bias is measured from dark emulator, which is based on Dark Quest simulations. And this work was done to do a forecast for a kids-like survey and see how we can model this effect, and also if there are other ways to mitigate it. So this plot here is showing constraints on S8 and omega m. The data vector always has the nonlinear halo bias, as we know we have that in reality. But the model changes, and we can see how that would affect things. So if we have nonlinear halo bias, but we assume that it's only linear halo bias, analyze things, we get the orange contour, and you can see that it's biased both in omega m and S8. Then we thought, okay, what if we add an extra free parameter for the two halo terms? So the amplitude of the two halo term can be fitted to the data. And the result we get is the green contour. So this fixes the problem for omega m, but S8 becomes even more biased. And then if we add extra information through the stellar mass function, which tells us the abundance of galaxies, basically, that would shrink our contours, and it will fix our halo occupation distribution parameters, so how galaxies distribute the halos, which means that it will increase our biases by more than 5 sigma. So And the reason we added this information is because when you do such an analysis, there is a lot of degeneracies between parameters. And if you want to shrink your contours and get some information about how galaxies populate the halos, you need to add this extra information, and this is what we wanted to do with the actual kids data. So this shows that we really need to add the nonlinear halo bias to get unbiased results. Okay, so this is what we've done in this paper, which came out late last year. So, and this is using kids only data. So kids bright sample, which is similar to gamma survey, is used as the lenses. So is used for galaxy clustering and is used as lenses for galaxy-galaxy lensing. Then we have the halo model that was tested in Mahoney et al. And include stellar mass function. And this allows us to extract small scale information from the data. So now the interesting thing here is, so if you just look at the plot first, we have S8 versus omega m. Pink one is cosmic shear that we had before, and the blue one here is the new result. And then we have Planck in black. The purple one here, that's the smaller one, is the combined probe analysis for Kids 1000, so the one with BOSS. But if I go back to that analysis, if I go back 1 second, here, this blue contour here, which is just BOSS, is the same size as this blue contour here. And BOSS has 9 times the area of kids. But because we were able to push to smaller scales, we got basically the same constraining power as a huge survey like BOSS. So I think this was one of the biggest things about this paper that we found. And this is not combined with cosmic shear currently, so you can imagine how it would look like once you combine it with cosmic shear just by eye, how it would look like. Of course, there is cross-covariance between the terms, and you have to take that into account. Okay, now how does this result compare with previous work? So you have S8 and omega m here. This is the results from Andre's paper here. And then we have one of the earliest results that used kind of a similar method from SDSS. And then we have combination of coefficients with BOSS, and this year 3 results, which use there's only data. Then we have combination of hypersuprime cam and BOSS, and then this is the Kids 1000 core cosmology results, and so on. So you can see that it is relatively consistent with all the other results. And it is, again, S8 is lower than the value that Planck finds. So it's a consistent picture that we're getting here in general. Okay, so aside from that, we can also use information from higher order statistics. So far what I've shown you is using just information from 2-point statistics. And basically power spectra only. But we can use information from, for example, density split statistics. This is a paper by Pierre Berger. And here you can see the results from that. So this is again using the Kids bright sample. And the signal that isn't here is like galaxy-galaxy lensing, but it's galaxy-galaxy lensing that's been divided into density bins based on the line of sight. So the denser line of sight are averaged together, and then the less dense ones together. So it's, I think, 4 bins in density. And then this is also combined with just a correlation between the densities in line of sight as well. So that's the NAP part here. So this is using aperture map statistics, if you're familiar with that. Now you can see again the combination of S8 and omega M, cosmic shear results in orange here, Planck in red, and then the new results are shown in black. Again, this is not combined with cosmic shear, and you can imagine how it would look like once you combine it with cosmic shear, but it's giving competitive results when we compare it to the previous work, which was using only 2-point statistics. And all of these can, in principle, be combined together as well to give tighter constraints. But again, you can see that this is a consistent picture that we're getting here. S8 consistently stays lower than Planck, no matter what kind of analysis we do. Okay, and then we have this latest result, which will be, I think, submitted tomorrow. And this is looking at changing something about the modeling. So, and that is the halo mass function. So how halos are, how many halos of each mass we have. So the fiducial model for analyzing the data is using the fiducial model that kids used, so that's HM code, and that's like an augmented halo model, which matches the simulations very well. But all the other choices are matching the surveys. So there are 2 surveys used here. We have Kids 1000 as also this year 3. So you can see the fiducial results choosing this combination for both of them. So we have this Y3 in blue, so lion, and then we have the Kids one in pinky salmon color. Now, if we allow for the halo mass function parameters to vary, we get these 2 contours that are bigger. So we have the bigger blue and the bigger red contours. And the Planck results are shown in gray. Now, the interesting thing is that although the contours get bigger, their central point doesn't move up. And when we look at the fit to the parameters of halo mass function, if we fix everything else, if you fix everything else, they actually prefer the fiducial values for the parameters. So the fiducial values of the parameters do actually match the data pretty well. So we don't have any smoking gun evidence that the fiducial parameters for halo mass function are wrong. But if we fix the cosmology to Planck, we get different values for the halo mass function. So in principle, something like the halo mass function could resolve the tension. But with this analysis, we can't say that it is definitely the halo mass function that is not modeled correctly. Okay, and then we also see that these parameters have a lot of degeneracy with sigma 8. So it makes sense to look into them a bit better, a bit more. Okay, and then finally, an analysis that will be coming out soon. This is combining Kids 1000 and this year 3. This is done by both teams together, working together. So the analysis is done assuming all the shapes and the redshifts are the same. But what we've done is to really assess the modeling choices and what impact they have. And then coming up with the hybrid analysis choice, which we think is the best analysis choice currently. And then analyze both data. So the core team you can see here is a combination of people in DES and kids. And the analysis is basically done. So we're just writing the paper now, and it should be out, I don't know, in a couple of months or something. Famous last words, maybe. Okay, so I'll just summarize. Cosmic shear analysis give consistent results with each other. It's also true when we combine cosmic shear with other large-scale structure probes or compare them with the results of other large-scale structure probes. we consistently find lower values of S8 when we compare to applying 2018. And then the other thing is that try to do all your analysis blind if possible, and think about how you're going to blind your data before you start analyzing it. Yeah, and finally, it's exciting times to do recleansing and combined probe analysis. And thank you very much.
Thank you so much. Very, very nice talk. Do you have any questions? Yes, Erin.
Hey, Marika, thanks very much for a nice talk and the explanations at the beginning. If we go back to basics, right, in cosmology and the Friedmann equations, more or less what it tells you is that if you have the wrong cosmological model, you expect H0 to evolve with effective redshift. So that's a very simple statement you get from the Friedmann equations. Now, we have persistent cosmological tension, so it looks like the lambda CDM model is breaking down. Now, if you basically take the lambda CDM model and fit it to, say, supernovae data or quasar data or anything that you can essentially bin in redshifts, what you find is you find a descending H0 trend with effective redshift and an increasing omega M0 trend with effective redshift. Okay, so we're finding this in a number of places. Now, what that would imply then is that S8 would also be evolving with effective redshift. Now, there is some, if you compare HSE to DES to kids, there seems to be some small little discrepancies in the redshifts of the bins, right? So it's my understanding that HSE is at slightly higher redshifts than, say, DES or kids. I mean, maybe in some study it's 4 bins, some studies it's 5 bins, but there seems to be some hint of something going on there. I think you showed a plot where omega M, you had S8 and omega M for HSE. It's a later plot than this.
Oh, yeah.
And there's sort of like, if we see it in supernovae and you know that this should be happening if the tensions are physical, you know, you have a strong argument there from theory. And we find it in supernovae, we see it in quasar data, we see it in observational Hubble data. Then you're going to find it in cosmic shear, but it's a question of whether or not the statistics are sensitive to this or not.
Yeah,
now, it's curious that HSE is giving you a high omega M here. And my understanding is HSE has, you know, if you look at the tomographic bins, they're shifted to higher redshifts than kids. Is that?
Yeah, HSC is deeper than the other two, although they don't use all the data that they have because they find it difficult to calibrate the deeper bins. The thing is, if you look at the cosmic shear alone results, they are all consistent because we expect to see 1 sigma deviations. And also the other thing you have to take care of is that the choices that the people have done in each of the analysis is different. Even taking care of like redshift calibration and so on, the modeling choices are different. This is what we found when we were doing the kids and dads analysis together. Once we use the same analysis choices, we find results that are different to what you see, say, here. So if you want to actually do that kind of comparison, you have to kind of sit there and see, okay, how did you model intrinsic alignments? What did you use for your power spectra? And then match everything. Once you've done that, then maybe you can make this statement. Now we're doing that for kids and dads, and there was a paper recently by the LSST team who did that for Kids 1000 this year 1 and HSC. And that would be a good one to look at because they actually use the same modeling for everything. And I think it's an interesting thing to look at to see what S8 is per redshift, but the current data is not quite sensitive enough. Maybe if you combine all of them and then bin things, then you can get some indication. But I think as it stands, it's difficult to say if it's actually there or if it's because
Right. Good. And just on that note, as long as you use the same assumptions throughout, you know, no matter how you're modeling, as long as your modeling assumptions are the same. So to give you an example, strong lensing time delay, depending on how they model their lenses, you can find a descending H0 trend across the lenses. This is documented in the first Holly-Kayo paper, I think in the appendix, the first one that confirms Reese's value. So yeah, there's other things there. So I would really expect to see an increasing S8 trend as you push deeper in effective redshift across your analysis.
Mm-hmm.
I mean, this is the claim. And if you see it in supernovae and you don't see it in cosmic shear, you're getting buried in nuisance parameters and getting buried in statistics. I mean, supernovae is essentially as simple as it gets, right?
Yeah, exactly. So I think that's the key point, is because the modeling can be quite complex. It can be a little bit difficult to see it in just looking at the results. You have to dig into the details before you can say anything conclusive. That's why I think that's basically was the take-home message from this work we've done with kids and Des, which we thought at the start would take only a couple of months, but it's more than a year past, and we're still working on it.
Okay. Thanks very much. Thank you.
Thank you. Bozzena?
I have a very basic question because I'm not sure I really follow the situation. Is this tension really arising because we have problems in description of the baryonic matter and its behavior? So is this problem really related to the baryonic matter behavior, while the dark matter behaves, let's say, fine? Can we tell anything about that? Where is the core of the problem?
So there's been some claim that it could be just a baryonic matter, so baryon feedback in particular. But when you compare the baryon feedback levels that are needed to match the cosmic shear results to applying, it's very high. So it's higher than any of the simulations that have been giving predictions that match with data. So it is unlikely to be just baryonic matter that could cause this. But to be able to say conclusively if it is dark matter or not, we need to have a good handle of how the baryonic matter behaves. So it's important to focus on that. Although cosmic shear is more directly probing matter, so it doesn't rely on bias tracers like galaxy clustering, is still affected by baryonic matter behavior, for example, intrinsic alignments and baryon feedback. And because we're getting more precision, it's getting more and more important to understand these two. But my guess is that it's not baryonic effects that can explain this whole thing.
Okay,
if I jump in there, Marika, just if you see something in supernovae, it doesn't care if it's baryonic or whatever, right? It doesn't care if it's dark matter. You're just fitting the lambda CDM model, and it's a matter density, and you don't distinguish. So I agree with Marika. I think you're not going to, baryonic effects aren't going to explain this.
No, I mean, especially if you want to explain H naught problem and S8 together, then it would be difficult.
Actually, just on that, Marika, just if H0 is evolving, the S8 problem, the H0 problem are not independent. It's very difficult to disentangle them.
Yeah.
Because once H0 is evolving, Omega in the late universe, if it happens in the late universe, Omega M is evolving, and then S8, everything is just. And so I think this is the problem with a lot of theory that's going on in the literature at the moment. There's an implicit assumption that Omega M is a constant.
Yes, that's true. Well, you can get omega M varying if you have, say, these interacting dark matter dark energy models. Then you get that.
Yes, but what I mean that there's a constant, there's a fitting parameter omega M0 that corresponds to, or you could even say it's omega B0 or omega C0. It doesn't make a difference, but we're implicitly assuming that matter at high redshift sort of scales as a to the -3. And I don't think anybody in cosmology has checked that. Has anybody shown that that's correct? Data is improving rapidly, but I don't think anybody has basically done that study.
I think this is something that we are trying
Bit
to...
off topic.
Yeah, so we are trying to fit the data with different models and see if they improve or not the fit. Okay, there is another question, Shri.
Yeah, hi. Thanks, Marika. Marika, can you just go back to when you were discussing the Halo model, the 1 Halo and 2 Halo model, and you had a slide where you showed how the values, yeah, exactly. Oh, sorry, no. Just where you had the results of sigma 8 and SM with different Halo terms.
Mhm.
Yeah. So I've been trying to actually understand this for some time, and maybe you can help me with this. If you look here, if you include like free 2H parameters or nonlinear terms with S star, I assume that's SMF is star
Stellar mass function.
stellar mass
Yeah.
function, right?
Yeah.
So in the graph, I can see that it overestimates sigma m, but it consistently underestimates S8.
Mhm.
Like if your model has more parameters, it starts to overestimate sigma m, but it, regardless of that, it always underestimates S8. So like what is going on here, and like why does this go in such different directions? Like it never overestimates S8 under any circumstance.
Yeah, I think this is probably because of this plot here. And where the signal is coming from, it's probably this dip here where we are most sensitive to. And this always stays like this no matter what you do to your model. And I think we thought that allowing for the two halo mode to be free could resolve this, but obviously there is some sort of degeneracy that's broken and it doesn't allow it to go higher. And I think that's what's happening here. So I think it's this dip here that's causing
So this would be this would be about how much would this be, like 10 megaparsec? I mean, like what would the inverse scale in real space would be for this? Just an estimate.
Real space. But it is the scale that we're more sensitive to, around here
I see.
somewhere. Yeah.
Okay. Okay.
Yeah.
I see.
There are some other plots in the paper that look at the impact on the actual observables, and that might make it a little bit clearer what's happening there. I don't have them here now. Yes, because this is power spectra,
sure.
but we're not like actually looking at power spectra. We're looking at correlation functions. And
Yes.
there's a range there, and that range you can see like how, if you change things, how that changes. I think if you look at that, maybe it will be clearer. Yeah.
Okay. Yeah. Thanks.
Okay, thank you. Any other questions? Yeah, Marit.
Marika, thank you for a very interesting talk. But about this, the approximately 10 megaparsec scale and correlation function and power spectra. We have shown in our papers that this scale is very sensitive also to the presence of voids in the sample, not just halos. And what you call as two halo term, it's more like related to structures between halos, like filaments of galaxies and voids. And this also has been properly, it should be taken into account correctly in analysis. I will send you some references after that, but you can check. It is just series of recent paper by Jan Einast and myself about the correlation function, power spectra, biasing, and so on.
All right. Okay. Yeah. Thank you.
Thank you.
Okay. Any other questions? I think there is a comment of Tamara. Tamara, maybe you can comment this so it can be recorded for people who are not here. Maybe I can read it. I've tried to fit the supernovae data to omega m a to the -3 constant that is not 3, sorry, and none of the other exponents I tried improved on the basic one, but that's not an exhaustive search of functional forms, although we did look at a bunch of other functional forms too. Saying omega matter is not constant is confusing though, because we know it's not constant. Okay, I think that you.
What I mean is the fitting parameter is not a constant. The omega m0 is not a constant. So that's the assumption cosmologists are always making. And basically, if you try to basically, okay, so what's been shown in the Hubble tension literature is basically if you assume omega m0 is a constant and you allow the dark energy sector to vary, typically it's very difficult to get a H0 over 70 kilometers per second per megaparsec. I mean, I think George has shown this, George Efstatio. There's various other groups who've done this. We've done our own study on this. And it's a strong assumption, but I think it's an assumption that goes into modeling.
By omega m0 is defined at 0 redshift, isn't it by definition?
Well, no, it's a fitting parameter, right? Planck fitted to data, right? Everybody fits it to data. So for example, like the confusion here is that H0 is an integration constant. We define it at z equals 0. That's a mathematical statement. That's not an observational statement. So what cosmologists are doing all the time is conflating mathematics with observation. And what we need to check is whether or not H0 is actually a constant.
No, the point, okay, I agree with Marika here. So we defined H0 and omega matter at redshift 0. Okay, and
that's fine, but it's a fitting parameter in your model.
Yeah, but this is a definition, like Tamara is saying, okay, then this evolves in a certain way, and we can discuss how this evolves, but H0 and omega matter 0 are the values today.
No, so that's not technically speaking correct, right? So for example, let's go back to H0. When you solve the Friedmann equations, the Friedmann equation is a first order ODE, ordinary differential equation. You have to specify H at some Z to solve that equation. So what we typically do is we put in H0, right? But all that does is introduce a fitting parameter for you. And it's universal to all FLRW cosmologies. So now you can take your, whatever data you have at any Z, and you can basically fit H0 to it. This is essentially what Holly Cow are doing, because their lens systems have different effective redshifts, right? And they're finding a slightly descending trend of H0 with Z, with the lens redshift.
Okay, I think
it's a sort of, I'm happy to give a talk on this, Eleonora. I think it will clear up a lot of, misconceptions in the literature. And then
I'm pretty sure that H0 and omega matter are defined today at z equals 0.
No, that's true, they are. But
okay, this is another thing. Is H.
But they're also fitting parameters, and the question is, do you bin your data or not? That's the question, right? If you bin your data, you can find evolution in these fitting parameters.
No, when you assume...
it's true. So if say that your model is not correct,
right,
then you look at different redshifts, you find different H0 or different.
Right. Good.
That doesn't mean S8 is varying. It means your model is not correct.
It means your models, but basically, if you do all your inferences within lambda CDM, which is the wrong model, then you expect the evolution.
Yeah, if it's the wrong model, then it shouldn't be surprising if you don't get the same value.
Right. And so what Hubble tension tells us at some level is we have a late universe H0 determination, an early universe H0 determination, and we can change the experiments, right? We can have different local determinations, and we can get rid of Planck and replace it with, BBN and, other experiments, but we still have that discrepancy. So this, tells you that there's a problem in redshift. Now you need to confirm that by filling in the redshifts in between. And once you do that, you're done. You eliminate systematics then as the problem.
Yeah, I think Tamara think that we are a bit off topic, yes.
we're off topic. It's a discussion for another time. Thank you, Marika. Thank you very much for the talk. Eleonora, thank you very much for hosting.
Thank you for the discussion.
Okay, so thanks a lot again.